So, in order to tell if something converges, what could we look for to see if it converges? What kind of things do we know converge? All right, so if it's decreasing and it's bounded below, if it's decreasing and bounded below, then that must be, so if it's monotonic, or strictly monotonic, decreasing and bounded, or similarly if it's increasing always, or at least never decreasing and bounded above, those are two situations we could look for, right? Anything else we know that would tell me? I mean, I think somebody might have just said it. I mean, how do I know that this is convergent? How would I know that's convergent? Because the limit as n goes to infinity of that is something, right? So that's definitely convergent. So I really want to make this distinction now because people get confused. For sequences to converge, their terms just have to go to a number, a finite something, right? Because the only way that a sequence could diverge is if the terms go to infinity or negative infinity. Are you guys with me? When we start to look at series, and how does series relate to sequences? I'm not talking about your Apple phones lined up and you talk to all of them at once. Not that kind of series. But series, how does it relate? Consider I just made that up right there. It's not that bad. Thank you so much. Yeah, right, whatever. Now it's just silly. So how does series, why do we call certain things series and certain things sequences? What's the difference? Series involves... I think you said it. I couldn't hear you.
Isn't series just a list of numbers?
Series is your adders.
Yes, series involves addition of the elements, right? So sequence involves just listing the elements, 1, 4, 7. Series would involve a sum of those elements, right? You guys kind of with me? So for a series to be convergent, it's even worse. And then we're going to talk a little bit, we're going to fill in some gaps today as far as in order for a series to converge, what must the elements do of that sequence that makes that series? All right, so let's come back down. So this guy, I could just look at him as limit. Why would a limit not necessarily work here? Or would it?
I don't know. I was thinking it'd be the comparison thing where you kind of like broke it up. And
Sure, you could do that. If you could create another sequence that you know converges. Sure, you could do that.
wouldn't it be like you take off the sign 2n and you got the 1 over 1 plus?
So let's build that up. And I was trying to see if they had discussed that here somewhere. Did I miss that? No, that's squeeze theorem. Well, I'll show you anyway what you're trying to do. So if there was a Bn where An was always smaller than Bn, right? This is like we were talking about before with the. Just trying to see if it's not even trying to see if it's bounded, but just trying to see if I could find something above it that converges, then it must also converge. So if I feel, now why would I think this converges? Because what does sine of 2n do? It goes in between -1 and 1, right? But what does 1 plus the square root of n do as n gets big? Gets crazy big. So the bottom is unbounded and the top is bounded. So it should go to 0. I feel like this should converge. But the limit won't really help because it's an oscillatory thing. Right? And limits don't really play well with those because there is no limit for those. They have no limit, but that's an example of no limit, but it doesn't go to infinity. It just doesn't go anywhere. It doesn't go to a single place. How are we doing so far? So it's not a bad idea because sine, of course, is definitely bounded. We did an example like that the other day. So what is this always less than? An is always or at most 1 over 1 plus root n. And what's the limit as n goes to infinity of 1 over 1 plus root n? 0. So since an is always at most this, and this series converges, this series must also converge. It's like push down. I don't want to converge. I don't care. It just kills it.
that's what I had. I just didn't think.
Kicks ass. It's perfect. I love it. Okay. Why would L'Hopital's maybe not do me much good here? Because the derivative sign is, and I still have the oscillatory problem, right? So that might not be a great idea, right? And plus, why can't I use L'Hopital's in the first place? It's not indeterminate. I love it, right? It's not 0 over 0, infinity to 0. It's just, I can't decide over infinity. So that's not even indeterminate. And to be full openness. As a student, I didn't even want to do this, because I was saying sine 2n is basically a freaking number. Yeah. A number over this is going to go to 0, leave me alone. So if you want to say that, I understand your desire. But this is not that hard to show, and it gets you a little used to how to think for this test, because then you're going to hit stuff that you got to use this test for. You can't just look at it and I know what's going to go on. Cool. All right, good. Okay. Anything else? Yeah.
Could we also just calculate an of the 54, same section?
54?
Yeah, I just couldn't figure out the an of it.
Oh, yeah, okay. Well, okay, so let's see. That
it's
one.
Like adding 2 to the denominator, then minusing 1, and adding 2.
So let's see. 54's got this list. So I don't know if you guys have looked at this one yet.
Yeah.
You, I know. Well, what's your gut instinct when you first look at this thing? What do you think is true? Do you think it's going to be convergent before we even try to figure out an expression for it?
I think it is. It's going to go to 1 over infinity.
Yeah, it looks like it's bouncing around, but it is sort of bouncing around in an increasing way on the bottom, right? So the whole thing's going to go to 0, it looks like. If I try to write an expression for this, it gets a little freaky, to say the least. But look at this. Here's 1, 2, 3, 4. And here's 3, 4, 5, 6. Do you guys see how every other one does something? I think that's what you're trying to say, right? Yeah. Okay. So if I look at these, that looks pretty simple, right? Mm-hmm. If only that was A1 and A2, but that's actually A3. So what's another way I could do? And these would be pretty damn simple, right? If only. So what you said is interesting. You said it goes up by 2, then down by 1, then up by 2, then down by 1. Right? Good. So let me introduce something into the mix here. I want you guys to think about this. What would this do? Yeah, it would be positive for one, negative for the next, right? Yeah. So it would be interesting if, let's see, how can I build this up? So there might be a way, and this is just my own curiosity, I think, there might be a way to use this. I mean, you can start thinking like, if I do twice this, or even just this plus 1, what would that do?
0.
If n is odd, this will be 0. If n is even, this will be 2, right? This is sort of getting closer to what this thing is kind of doing. I don't know if you guys see what I'm saying. I mean, in another sense, you could actually do this in a very kind of cheaty way and say, if I have n is odd, that's one thing. And if I have n is even, that's another thing, right? But you do kind of want to have one cohesive definition for the whole thing. So I'm thinking this is definitely possibly, you got to play with this a little bit more to see if you can make it happen. That might be one way to do this. Another thing to consider is these might be reduced forms of something, right? I think this would work, but it might be like 2/4. You know, maybe that kind of makes it easier to do something with. This doesn't, to me, it doesn't look like it's going to be that, but sometimes it happens with fractions. They just reduced, and if you build them back up, you can see the pattern very easily.
Yeah.
So that happens sometimes. Here, it just doesn't feel to me like that's what's going on, because there's a definite pattern in every other one. Right? So it's got to be something that kind of turns on and off, and that's the most basic turn on and off kind of thing. Or this is actually like go one way or the other way. So I'm trying to give you enough tools to kind of work on this. I don't want to say anything too much until I had more than one person that worked on it. So I would try this. Now the question doesn't ask you to create a form for this, right? The question just says, determine whether it converges or diverges. And I like this question, though, as far as trying to create an expression out of it. Because you do see ones that have every other one does something. And if we could create an expression, then the question's easy. But even without it, the question's pretty easy. I can see that they are decreasing. They are definitely decreasing. You know, if I look at every other one, both internal sequences are decreasing, so the whole thing is going to decrease. So for this problem, it's good enough to say that. But I do like that you're trying to figure out an expression for the whole thing. Yeah. This guy, and again, it's very often a question of realizing what you're allowed to use. Yeah, and this little dude actually works, even if nothing's negative, he could work to turn something on, turn something off. I don't know if you guys see what I'm saying. Like if I did this +3, what would that do? So if the n is odd, this would be 2. If n is even, this would be 4, right? So it's kind of like turning on the +4 and then turning on the +2. Turning on the +4. Okay, maybe. So that might help you. Okay. Well, for this question by itself, you just have to point out that there definitely seems to be decreasing there, and this is definitely decreasing also. So overall, the whole thing is definitely decreasing. Yeah.
Would you consider it incorrect to do the odd and even separate?
No, that's what I was just saying. That does feel like you're cheating a little bit, but there's actually absolutely nothing wrong with that, because some sequences just have that happen, and there's nothing that really connects them. Here, I just feel like there is something that connects them. Okay. So if you realize what I just said, you don't have to go as far as that for this problem, because it doesn't ask you to. But I really like that problem, so maybe that's a motivation to try it out. Okay. Anything else from homework? I don't know, did I? I feel it sounds familiar. Did we just do that? 7, 7, 20? Oh, yeah. Yeah, we talked about that to a point.
No, I remember now, yeah.
Yeah.
Actually, I got one. 7, 8, number 30.
Number 30. Okay. Oh, yeah. Okay, good. I'm not going to, if you look at this section, they define types of improperness, right? So they have improper integral type 1, improper integral type 2. I don't care about all that.
This is like type 2.
Yeah, it doesn't really matter. I mean, yeah, all I care about is, I don't care if you know, because you look at a different book, they're going to call the type 1, type 2 the other way around. It's not a set thing. There are two ways to have an improper integral, and the reason we call it improper is it doesn't match the definition. Right? We looked at the definition before for what an integral requires to exist, and this, when I have an improper integral that does not meet that definition, I can still attack it, but I have to use limits. So in a few of the homeworks I've graded from this section, people went through, I never want to see something like this. On one step you got that, on the next step you got that. I never want to see that, because what's infinity squared? You could plug a value in, but what is infinity? What is infinity?
It's not a number.
It's not a number.
It's an idea.
It's not a number.
Constants.
It's a process, right? Infinity describes just keep going up, just keep going. So I can't plug infinity in. The same way I love it when I have students that find infinity on a number line. That's neat, right? That's their like telling you that's like finding nirvana. You gotta let me know when it happens. You pass this on another plane, you sort of disappear. So if you want it to happen, try to find infinity on the number line. So let's see, which one was this? All that talking, I forgot. 30, right? Yeah, exactly. So obviously, which side does this thing have a problem with? Yeah, so it's got a problem there.
Could you come from the positive side?
Yeah, because you exist between 6 and 8, so you don't exist below 6.
Okay.
So when you do your limit, and the function itself exists on the other side of 6, but in terms of this integral, you can be more specific and say like this. And the whole, I really want to make this make sense. The whole reason we do this, that's a plus sign. The whole reason we do this is so that I don't have to plug infinity in. I plug t, that's infinity's proxy. T is a number. The value of t is growing, but t itself is some number. And of course, how do I do this integral here? This is linear, so it's awesome. It's just like 1 over x cubed.
Move it to the top, so make it all back to the negative third.
Okay, sure. And then what happens?
Or just constant.
I think I pulled out the 4.
Good. 4 comes out.
Yeah, so I just have.
You'll get x minus 6 to the. So here it's negative 3, right?
Yeah.
So when you integrate, you'll get x minus 6 to the
Negative 2.
negative 2
Yeah. All
over
over 2. Negative 2.
negative 2. Cool. So don't make a big deal out of x minus 6. That's like x. Shifted, who cares? So it should be easy. Even 2x minus 6 in there would still be easy. We just have to divide by an extra 2 that would come popping out, right? And still, any linear thing should be relatively easy to integrate. So what happens?
I have a question. I tried doing U sub in the beginning. Would it be more practical to do U sub or just...
No, well, U sub is not bad. I mean,
That's
when the U sub comes out like that, it's actually trying to tell you, I don't want to see, there's nothing wrong with that. But when U sub comes out like that, it's trying to tell you, you don't really need me, dude. Right? du is dx. I'm not a major shift. I'm not a major, but if it does make it look better,
Yeah.
right? Because then you'll have 4 over u cubed, which is 4u negative 3, which integrates easily. I'm trying to get you guys to the point where you look at x minus 6 itself, that's just a number. That's you know, so integral of x minus 6 negative 3 would just be that. It's not, yeah, but if you need that, it's no problem. Extra practice on u sub, I'm not going to knock that down. And now I just plug stuff in. So here I get negative 2 here, right? Times
2 squared and 2 to the
2 to negative 2. Good?
Yeah.
Minus, actually plus 2 times t minus 6 to the negative 2. Is that cool? So this is finite, but what happens when I try to plug 6 in here?
0.
So it's 2 over 0, isn't it? That's a negative power, right?
Yeah.
So that part would go to infinity. So this would be infinity, this is divergent. This limit would be infinite. This is a divergent integral. So it starts off as improper. It still has a chance to converge. But after the work we saw, oh yeah, this is divergent. Okay? Where did I do that?
Could you simplify it further?
I plugged an 8 in, and I plugged a t
And what
in.
did you just
put it like 1 over x minus 6 before you plug it.
Oh, sure, you could. Either way, it tells you the same thing.
Oh, because when it's
Yeah, when it goes to 6, this is going to go to 0, 1 over 0, infinite. So anything else from homework? All right, I'm going to take that as a no.
So that's what we do.
Any other questions on that one? Are we good with that? Have we broken off into other? Did you think I was choking? Talk amongst yourselves. Yeah.
You said if it's undefined, it goes to infinity, right?
Well, undefined is our algebra attempt of saying infinity in one way, right? 1 over 0, we say it's undefined. When you get to calculus, one place 1 over 0 could come from is the bottom approaches 0. And we understand that process is the same thing as the whole thing approaching infinity. Cool. In algebra, though, you just try to plug a 0 in and you call it undefined because there is no number defined to be what 1 divided by 0 is. Right? Yeah. 68 in 11.1. Oh, here we go. Perfect. That kicks ass. Oh, sorry. If you look at number 68, it has a sequence defined piecewise based on if the n is odd or even. Beautiful. All right, so that's completely happens in real life and in the fake life of math. It happens. Right, that's the one we're looking at, Sabah? Or am I just... The one that says, find the first 40 terms. An plus 1 equals... Gotcha, okay. So this is number 68, 11.1. Even. All right, so two things here. This is a recursive. This is recursive. I've used that word maybe once. And recursive means it's a function, and we talked about it with Fibonacci. Recursive definition of a sequence is where the next element is based on previous elements. So this one says the next element, if the previous element was even, then the next element would be 1/2 of that thing. If the previous element entry was odd, then it's going to be this. So the first thing they tell us to do, thank God, is write some elements out. I mean, that's an excellent thing to do when you have this facing you. I want to see what the hell it looks like.
So this is like an example where you're saying when n breaks up the even.
Beautiful.
Right?
I love it. Exactly. A1 is 11. So they want you to write out the first... Oh, okay. Find the first 40 terms of the sequence. I don't think we have to write them all out. We're going to see a pattern, hopefully. Make a conjecture about the subsequence. So A1 is 11. So n here is odd. So to find A2, what am I going to do to 11? Good. I'm going to use this one, right? Careful. N. If I want A2, n is 1. You with me? 1 is odd, so I want to use the one for the odd stuff. You with me? So if the previous sequence element had an index that was odd, I'm going to use this guy. And then I'll use this guy. This is this. So 3 times 11 plus 1? 34. So A3, what do I want to do to this?
1/2.
Cut it in half. A4, what am I going to do with this?
3 plus 1.
Yeah, 3 times that. What's 3 times that? 51. Plus 1 is 52. And then I want to do what to that? Cut it in half. Are you guys? Yes?
I mean, I did look at the answer. I mean, I did look at the question in the book, but did they give you A1?
Yes, they have to.
Okay.
Any recursive formula, they have to give you a starting point. If I say, to get to the next one, you add 3 to the first one, and I don't tell you what the first one is, I like that. I'm just pulling them out my ass like I normally do. Let's say 6. Yeah, 3 times 26. 3 times 26 is 78 plus 1. All right, and then I would cut it in half. Yeah, so if I cut this in half, 39.5. Yeah, gruesome. So hopefully I didn't make a mistake there. Yeah, they gave us 11. Good. And then A2 would be 3 times that plus 1. A3 is half of that. A4 is 3 times that plus 1. Good. Half of that. No. Help me out. If n is even, n, and what the hell is n? What's n for this guy? 3. Yeah, for this guy, well, it's 2. It's the previous one, right? I like that. So this would be an plus 1. If I want to find a3, that means n is 2. That's even. That's why I had to cut this guy in half, because it's half of an. Okay. All right. Now, you shouldn't have to write 40 of these sequence elements out. So, do you guys see a pattern? I mean, what kind of patterns can you try to see here?
Maybe n2 plus the n3, like 34 plus 17.
34 plus 17 is 51, which is 1 off from that. Right? 52 plus 26, though, would be 88. Kind of goes away from there, right?
Yeah.
Okay. And another thing you can try to find is this goes up by 23 and then down by 17, but then it goes up by what do you got here? 35, and then it goes down by 26. So I don't see anything there. I'm pretty sure they don't intend for you to write out all 40 terms. That would drive me a little crazy. Let's see what 25 does. Let's see between these two. If I start with 25, what's A2 going to be? So now the previous one was odd, so what am I going to do to 25? Triplet and add 1. 76. So now I'll cut it in half. 38. So now I'll do triplet plus 1. Good. And then I want to cut it in half. That's like where I want to stop. And then A6, I would triplet and add 1. All right, so whatever that was going to be. 51, 71, 172.5. 170, oh, plus 1. 173. Is that after the plus 1?
Yes, after the plus 1.
Okay, thank you. And then cut it in half. Yeah. So does it look like this thing is convergent? Yeah, you could kind of talk yourself out of that if you're not careful. You could say, well, that's like almost the same size as that, but every other one, of course, is getting bigger because both of these, the 1/2 kind of makes it that its own little sequence in the middle here. So if I look in the middle here, this goes up by 6, This goes up by 9. This goes up by 13 and a half. There's no pattern there, but sometimes there could be a pattern there. But at least that establishes it's increasing on its own. So it's like that one we saw earlier where there were two interior sequences and they were both getting smaller. So I knew the whole thing was going to converge. This looks like the opposite situation. This is definitely going to diverge. That's one thing I could say. For both cases, obviously, right? Now let's see what he does. What are the others? This goes up by 18, and then it goes up by 27, and then whatever the next one would be. All right, so this is the kind of stuff you can analyze when you get little sequences. This goes up by 13, whereas this one goes up by 39. That's interesting. Hey, look at that. Almost is in 6, 18, 9, 27. And then 13 and a half comes along and screws us up. Do you guys kind of see what I'm saying? That's not the point here, obviously, because that threw me off. But that's interesting. That's times 3 divided by 2 times 3. Oh, it is divided by 2. Hey, kick ass. Hey. Which kind of course, it makes sense because that's basically what you're doing, right? Times 3 divided by 2. Right. But what I would say about that is they're definitely both going to converge. I mean, diverge. They're going to infinity. I don't know what more they want you to say.
Do you actually want us to list all 40?
No, don't do that. Dear God, just get this far. Yeah. I did not want you to. That's just busy work at that point. I'm not going to do that to you. Okay. Now, to me, they should have started us off. If you start this process off with, a fraction, like if you started off with 1/3, what would that do? I mean, that would be what I'm more interested in. What kind of starting point could you do that would change? Could you make it convergent? Obviously, if you start with negative, it's going to just do what it's doing now, just in the negative direction. Does that make sense? But if I start with fractions, what would happen then? But it doesn't take you there, so I'm not going to take you there either. Okay. So I'd say just list out a few more than this. This is the kind of thing you could start looking at. Now, I like this. This is kind of cool. Does the same thing happen over here? We do this on both sides here, so it's sort of the same way. So that's 13. These two are 13 apart. These two are, what is that, 19 and a half? These two are 29.25. How far apart are these? Let's see. These are, I just had it over there. What did I say? 39? And then these are 60, let's see, 58.5. So that's 13 times 3 divided by 2 times 3. And again, just because of that. Okay. So anything else from homework? All right, cool. Let's get back into 11.2. I think yesterday we were talking about math induction. So if you missed yesterday, you desperately want to watch that video. We'll do, we did 1 and 2 last time, right?
Yeah.
So let's do number 3 together. 3 has this here. And another reason I wanted to show you number 3, has anybody not seen that notation there? Is that n plus 1? Yeah, what does that mean? It's exciting. So let's have a little side discussion here real quick. If I have 5 factorial, beautiful, 5 times 4 times, it's a useful tool. It shows up a lot in probability for counting the number of ways that something could happen. Right? You have 5 choices for the first slot, then you have 4 left after you pick somebody, you have 3 left after you pick somebody. So that shows up a lot in probability. So that's what that symbol means. So what is n plus 1 factorial if you try to write it out? And what if I wanted to stop there? How do I represent the rest of it? Yeah. So you can stop anywhere you want to, and the factorial really just says, keep going like this. I'm tired. Keep going like this. So we are going to do that every now and again, especially very soon when we start looking at whether a sequence converges or diverges. When it has a factorial in it, it's going to kind of be a hint that I want to do a certain test. So we're going to learn all these different tests to see when series converge or diverge. So it's a very nice test that sometimes I have to be able to do this so I can cancel some stuff out. So here, what's the very first thing I do, even if I don't know what the hell this is trying to say? What do I do first? It's my first thing I got to check. Yeah, got to do the base case. So what would the base case be in this case?
5.
Good. I got to start at 5, right? So if I put a 5 in there, 5 plus 1 factorial, the claim is that it's greater than that. So what is 5 plus 1 factorial?
6 factorial.
Yeah, 6 times 5 times 4, what?
720.
720. I love it. So if you do 6 times 5 times 4, you get 720. And what's 2 to the 5 plus 3? Which is 256. So in this case, 720 is bigger than 256. So the base case checks. So the base case really just says, show that for the first possible things, and last time it was all ones, this time it specifies 5. Show that for the first possible input for n, it's true. So establish that it's at least true for that. If you want to, you can put 6 in there just to see if it really holds up. What's my next step? So base case, first step. Good. Good. Assume that this is true for the kth element. So assume, I'm almost like reading the brains of people that weren't here last time. You're like, what?
K plus 1?
So assume that it's true for SK, which would say, assume SK is true. What would the K, you just put a K in there. Yeah, good. Assume it's true for some K that's in between 1 and n. Any K. So I know at the end, K is basically going to be the first one, because that's the one I know is true. But this is a separate proof. I want to prove that if it's true for one, any one, if I can show that the next one must be true, I know I said that a lot last time. If I could show that the next one must be true because this one is true, add that to the fact that I know the first one's true, I got them all. It's the whole dominoes thing I was trying to talk about. So these are 2 separate things. Show that it's true here. Show that if one of them is true, the next one must be true. Those together mean every damn thing is true. For any n above 5, or at least 5, it will be true. Whew. So what are we trying to show? That's the third thing I want to do. What we want to show what?
K plus 1.
And what would SK plus 1 be?
K plus 2. Plus
K
2.
plus 1.
K plus 4.
All right, good. Right? How are we doing so far? All right. So with inequalities, you actually have a little more flexibility with what you do as you go through this, which actually is both good and bad. capture all of you there? Okay. So this is what we want to show. We want to show. That's what we want to show. We can't use that for anything because that's what we want to end up at. But we can use this all day long. We know it's true because we assumed it was true. And that's where students are like, how the hell can you do that? Because the point of what I'm trying to prove is, if this was true, then this must be true. So that's why I'm allowed. Okay, let's say that's true. Let's see if the next thing would be true too. That's why I'm allowed to do that. That's a very relaxed fire alarm. I like that. You guys can leave or not.
I think that's more like, I think the fire alarm got set off by itself, so okay, join or something. Yeah. That relaxing sounds. Like,
So let's see. So the next step is start with SK. And actually, I'll show you what. With inequalities, you do something a little bit more interesting. I want to use this to show this, right? Yeah. So let's investigate, what is k plus 2 factorial? What is it? How could I write it in terms of something I know? Yeah, it's k plus 2 times k plus 1, and stop there. So I got to put the factorial, that means it would keep going, but I want to stop. And why would I want to stop here? Because I know something about k plus 1 factorial, right? What do I know about it?
Bigger than
Yeah, it's bigger than, so this is bigger than
2 plus 4.
2 to the k, no, careful. What do I know about, let me be careful. Sorry. Let me write this a little bit better. This is here. This product is bigger than this times 2 to the k plus 3. Let me stop right there. Let you guys catch up. So with inequalities, it's a little bit different. I actually want to start with this, investigate with it, and rewrite it so I can use what I know in it. So I said, okay, k plus 2 factorial. I want to be able to say something about that, but I can rewrite it in terms of what I know something about. Now, if I replace this with that, my expression is smaller than what it used to be because that's bigger than that. Let me let that sink in. So if I have 7 times 6, and I replace 6 with 8, let me go the same way. If I replace 6 with 5, what inequality can I put in the middle? Greater than, yeah, because this is bigger than that, right? So since this is bigger than that, this product must be bigger than that product. Same thing. Good. It's always nice to bring it back to just numbers so we can see what the hell's going on. All right, so keep going here. So I've already established that this, now look what this is the next thing we've got to get you real quick. I already established that this is greater than that. I can just follow the chain here, right? Now, if I can just show that this becomes greater than that, then I've got it. If this is greater than, now work, and get that to pop out, I'm golden. I've proven it. Some of you guys understand? Some of you guys are like, this is awesome.
How come you're not messing with the k that's above the 2? Like, how come you're not putting k plus 1 with that one?
I cannot. Because that's what I do here. I look at what the k plus 1 statement will be. But I can only work with what I know is true. We did the same thing before. Yeah. We started with what we assumed and then we added the next term on. Well, this is not an additive one, is it? This is an inequality one, which is pretty much always going to work like this. You start with this guy and you rewrite it so that you can use what you know. Now, let's keep going. What can I do on this side here? What's kind of nice that's in here that's going to get me closer to this? There's another 2 in there, isn't there? So if I multiply this in, what would I get? k times 2 to the k plus 3. Is that cool? Distribute. Now what's 2 to the k plus 3 times 2? 2 to the k plus 4. And that's what I want. Do I want this? No, I don't want that. But what's really nice is this whole thing, this number plus that is definitely bigger than this by itself. Let me say that again. This plus that is definitely bigger than this by itself. Because k is definitely positive. Right? So if I have this number plus some positive number, that's bigger than if I had this poor little number by himself. Now, have I gotten to where I wanted to be? I said that this is greater than this. Yes, there, I'm done. And that's the weird one. That step right there is where people freak out just a little bit because you're like, how can you just not write that now? Where'd it go? I said that that's greater than that. I'm golden. That's all I need to be able to say. So whenever I'm working with inequalities, you can have whole chunks of it fall off. As long as it's still true, it's greater than that. If I have this guy disappear, it's still true. Yes?
I don't see how you got 2 to the k plus 4 from 2 times 2 to the k plus 4.
All right. Before I cry. What's 2 to the first times 2 cubed?
2 to 4.
So what do you do with powers when you multiply them? When you're multiplying the same basis? Okay, good. So the weird part of this should be how this guy can go away. But it's because my requirement is just to show that that's greater than something else. I could do anything I want to this to make it greater here, or smaller here in that thing. Because that would still show what I want to show. That's what's really weird to people. We did something like that the other day when we tried to do the comparison test. And we had a 2, and we just dropped it off because it was less than something else. Or I think it was greater than something. I don't know if you guys remember that. We had a plus 2 on the bottom. We just dropped it off, made it bigger. Yes, sir?
So when it's equal, we have to get it back to the exact same thing, but with equalities, we just kind of have to show that.
We still have to. We still have to end up having on both sides one dude bigger than the other dude in this case, right? But in the middle, I can get all this extra crap. It's not necessary for the, this is not an equality statement. That's the key here. I just got to show something's bigger than something else. I don't care that it equals this. I just got to show that it's greater than something specific. So that's why I'm allowed to drop this part off, because then that would be greater than this. I don't have to show it's equal. Equal is a much more rigid requirement. That's why I said this is good and bad. This is good, because I can do all kinds of stuff, but that's why it's also bad, because we're not used to being able to do all kinds of stuff. Right? It's not an equality, it's just a greater than. So if I said 1 over n plus 2, and then I just drop the n away, what inequality symbol would go in the middle? Yeah, this side would be smaller than that, because here I'm dividing by more, right? Good. I mean, that's the kind of thing you could do in the middle of this proof here. Is that if you don't want that 2 there, make it go away. It's smaller than that now. Yay. But you gotta be careful. If I wanted to be... Now, here's the neat thing. You ready? No, you're not ready. Here's the neat thing. If I want to say it's greater than something... No, and this is what happens most often. In this case especially, because n is at least 5, I could say that that's greater than this. Let me just write that for a second, you guys. Is that true? Yeah, because 2 is definitely smaller than 5. So when I divide by n plus 2, that's going to be more than when I divide by 1 over n plus n. Right? Because I'm dividing by a bigger number here. So that's the kind of thing that you'll be allowed to do when you have a series of inequalities you're working with. You're totally allowed to do that. It's really freaky. That's more flexibility. It's why it's good and bad, because we're not used to it. And the only reason number 4 is almost just like number 1 and 2, except it's written in summation notation first. So how do I write the summation notation in 4 to make it look like what 1 and 2 have? So number 4 says, now this might be a stretch, but I don't know if you guys remember when you first learned Riemann sums. Do you remember when you had to do the summation notation and let n go to infinity? And in the process, you would have I, or I squared, or I cubed sum. And you had these 3 things. They're in the book if you want to go look back at it. And the one where they're squared was equal to this. That's exactly what it was equal to. Now, well, we can finally prove that's true. And you're like, I was fine before. I don't even, we can do it.
Yeah.
How would I write this to make it look more like 1 and 2? What does that sum break out to be? So 1 plus 4 plus 9 plus up to n squared, right? The largest input would be n, and that's supposed to equal n times n plus 1 times 2n plus 1 over 6. So now it looks a lot like 1 and 2. So then you're going to attack it with the same process. You start with the base case. You assume it's true for the kth one. So what would the base case say? How far do I want to go if n is 1? I want to go all the way up to 1. All right, so get used to that. It's a list of 1, but it's still a list. So the base case would say 1, because I can't get to 4 unless I let n go to 2, right? So 1, is that equal to 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6? Yes, because that's 1 times 2 times 3, which is 6 divided by 6 is 1. Check. Okay. Cool. All right, so base case is good. So I got my first domino to fall. And now I want to step back and say, let me show that if any domino falls, the next one must also fall. The 2 of those together means the whole thing works forever. Right? Okay. Just going to go a little quickly through this. So now I can say, assume Sk is true. And Sk would be 1 plus 4 plus k squared. K times k plus 1, 2k plus 1. Just put a k in there. That's why I'm being a little less careful. Just put a k inside there instead of an n. So now I want to show, what we want to show, Sk plus 1 is true. And what would Sk plus 1 say? Yep, wants to go up to k plus 1. And then that would have to equal, k plus 1, k plus 2. 2k plus 1 is 2k plus 2 plus 1 is 2k plus 3. All over, 6 dude just stays the same. He's not affected by anybody. It's just always a 6. This is what I assume is true, and this is what I want to show is true. And the reason I write this is just so I know when I know I'm done. When I see that, I'm like, oh good, I'm done. So then to do this, I start with what I know. So I know this is Sk. I know Sk is true. And I add what this says I need. So this says I need to add k plus 1 squared. So then I have what's on the other side. Plus k plus 1 squared. Now here's what's really cool. Some of you guys picked this up last time. This is the kind of stuff that I always loved, because you just force it, you just do what I want you to do, and then the rest of it's got to fall into place. And what do I mean by that? There's supposed to be a k plus 1 here, right? And see how there's k plus 1s there that I could pull out maybe if only I could get like an LCD, or let's do that first. So if I get an LCD between these two, it would be 6. Is that cool? Just multiply this by 6 on top and bottom so that I can combine them, just getting an LCD. Because that's currently over 1, right? Why am I doing that? Because that's what my form looks like. It's supposed to be all one thing over 6. That's what's awesome about this. You just use this as a goal. Now what happens if I pull a k plus 1 out? K times 2k plus 1 plus 6k plus 6. Is that cool? All over 6. And now what do you think you're going to do with all this stuff in here? Yeah, distribute like terms together, and I'll bet you anything it's going to factor like that. It has to. This is a known fact. So none of your answers for this kind of problem cannot be, actually it doesn't work. Because I'm going to start with, show that this true thing works, right? So it's got to work. Yes, ma'am?
For 6, don't we have like k plus 1 all square?
Oh, all right. So what did I do from this step to this step? I took a k plus 1 out. So that's why that k plus 1 is gone. And that has only one k plus 1 left that I gave a 6 to. I took a k. Now why the hell would I take a k plus 1 out? 2 reasons. I can, and the end result tells me there's supposed to be a k plus 1 sitting there by itself. That's what I love about these kind of problems. Just make a part of it do what it's supposed to do, and the rest of it has to fall into place. Kicks so much ass. Let it kick ass. And then this, you just distribute, factor, and you'll get these 2 things. If you don't believe me, you can do it. I'm not going to do it. I'm going to do like my old Cal teacher used to say, and the rest is algebra. So, continuing. Cool. All right, so now let's look at the other side. Maybe we'll look at the other side. Call it an ELFS, exercise left for the student. So here we're trying to define these infinite series. So like I said before, series are just sequences where I add up all the elements, right? So let the sum of an equal that, be an infinite series. So that's an infinite series just because it's going to infinity. You can see that there. So everybody looking on the other side of that paper. The nth partial sum is just if I stop at n. So that's like all these. This would be the kth partial sum, for example, right? So the 4th partial sum, I just add up to the 4th element and stop. Does that make sense by itself? The idea of partial sums. I think we talked about that last time. If the sequence of partial sums converges to a limit, then the infinite series converges. So we're going to investigate that more concretely right now. So as words, that doesn't mean much to us. Blah, 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 blah. Now here's the one good little thing that makes complete sense. In order for a sum of some sequence to converge, what definitely must be true about the elements of an? If you want, what's the easiest way to make it diverge? If you want it to diverge, what do you let an do? Get big, right? Even less than that. You could just make an be forever the same. If you just make an 2 forever. Well, if you add 2 up forever, you get to infinity, right? All right, so in order for this to converge, I can't let that happen. It can't stay the same. It can't increase. So it must actually decrease. And more specifically, it must go to 0. If the limit of an is not 0, I end up adding some concrete constant forever. That's always going to go to infinity. I don't care how small that thing is. You guys kind of... So remember, what was the most basic way I tried to show you concretely that you can have an infinite sum that does converge? I did this. Remember this? I love this example because it's so freaking concrete. That's an infinite series. Infinite. I just keep that up forever. But the answer is 1/9. Right? Because what do the elements do? What would the sequence go towards? What's the limit of the sequence? It is decreasing, but what is the limit? 0, right? It's 1/10, 1/100, 1/1000. That limit will definitely be 0. It's 1/10 to the n. If I let n go to infinity, that bad boy's going to 0. So that I can actually generalize that idea. For this to converge, the limit of my sequence elements has to be 0. If the limit of n going to infinity of an, if that limit of my sequence is not 0, then my series is convergent. What did I say? Yeah, divergent. Sorry. So if my series converges, then this is true. If this is not true, then my series is divergent. Yes, sir?
You said the series is convergent if the limit is 0. Why is not any constant?
Say it one more time.
You said the series is convergent if the limit is 0. Why is not any constant?
If it's a constant, and I'm adding that constant up forever, that's going to definitely go to infinity. So if I'm summing up, so if I have an and the limit of an is 2, you guys with me? If the limit is 2, then at some point I'm effectively adding 2 forever. Because what's it mean to have a limit of 2? That means at some point your elements get close to 2. So at some point I'm adding 2 forever. That's going to be freaking infinity. The only way I can add up a bunch of numbers that converges is if the numbers themselves get infinitely small. So they get out of their own way. I like that you get out of their own way because I just keep putting zeros out so it gets out of its own way. It doesn't like overlap and make itself get too big. Maybe. And I do want to be a little more careful here. I said this correctly, but I want to make sure you guys understand what this is. In order for this to have a chance to converge, this must be true. Now, you can have the limit going to 0, but this does not converge. That would be kind of evil. So, for this to have a chance to converge, the limit has to be 0. So, obviously, if the limit's not 0, it's divergent. It doesn't have a chance. Maybe. Okay. Oh, good. So let's look at a couple of these specific examples. Nice concrete numbers. Look at that first one there. Try to write out the first 5 elements. Just do that in a row. So do. So take this. The first problem is n goes from 1 to infinity. 1 over 2 to the n minus 1 over 2 to the n. So this by itself is a sequence, right? That by itself is a sequence. Adding that to it makes it a series. Write out the first 5 sequence elements. A1, A2, A3. What's up? for example, a sub 1 would be 1/2 minus 1/4. Is that by itself cool? Everybody got that first one? Good? I want to make sure we're off on the right track. Yep. 1/4 minus 1/8. So 1/8 minus 1/16 is 1/16. So I think by that point you can see the pattern. What's going on. So this next one's going to be
132, 164.
and real quick. If I just look at this, how can I subtract those? This is coming back to something from earlier. What do I need, of course, before I can subtract this? Elson, how do I make it? Well, this guy's got n plus 1 2's, he's only got n2, so he needs how many 2's does he have? N plus 1 of them. And how many 2's does he have? N of them. So how many more 2's does he need? Just one more. Good. So if I multiply by 2, I get 2 over 2 to the n plus 1 minus 1 over 2 to the n plus 1 is 1 over 2 to the n plus 1. And that's that sequence we see there. So sometimes you can take, sort of like when you have an integral and you're like, well, that's stupid. I could just divide it and the integral's easier. You just simplify the integral they gave you. Say, I'm not going to do yours, I'm going to simplify. So you could actually do that sometimes with how they give you sequences, or series in this case. Simplify it first, it's awesome. Now here's what S1 would be: the sum of all the elements up to the first element. All right, well, that's the first freaking element. So what's S2? Let me do this in difficult. So S1 is always the first sequence element because it only goes up that far. What's S2? And what does that S stand for? Sum. Those are the partial sums we're talking about. So S2 would be the sum of all the sequence elements up to the second one. So it'll be 1/4 plus 1/8 is 3/8. S3 be 3/8 plus 1/16. You can start to get smart about it, right? We've already got the sum of the first two. Just add in. So you have to double this to, right? So it'll be 6. So 7/16. And then that's 4. 15 32nd. And that's 5. 31/64. So I love it. Now, don't say anything out loud. Don't say anything out loud. Notice how many times I got to say. Sn. What would that be? This is really kind of cool. Of course, I might be the only one here that was that. So everybody notice something, and of course the more you do these, the more you know what to look for. So I'm not saying you should go into this chapter knowing what I'm about to say, but once you see a few of these things, you realize what you're able to look for. Does anybody see what's going on the top numerators? Something interesting about them. I mean, the first thing you try is, that went up by 2, and then it went up by 4, and then it went up by 8. Now that should kind of tell you something. Those sound interesting. Do it one more time. N over n plus 1, no.
2n plus 1.
2n plus 1. Over 2n plus 1.
S2, the numerator is just n.
You might be right, but you might be saying it wrong. I don't know. So isn't each of these one less than an interesting number? Plus 1 is 2, plus 1 is 4, plus 1 is 8. So these are all like multiples of 2. Not multiples of 2, but powers of 2. All right, so 2 to the n, but they're not 2 to the n. They're all 1 less. So why is 1? So that actually happens a decent amount, where they're 1 off from 3 to the n or 2 to the n. So it's always one thing. Now the bottom is just straight up something.
4n.
Let's see. Yeah. 1, 2, 3. So 4n. Now how does that not work? So that's no good. I thought maybe there's another way to do this than what I thought, but no. So I agree, 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is not 16.
2 to the n.
Yeah, but this is actually straight. Now you gotta be a little careful, not 2 to the n, because 2 to the first is 2. 2 to the, and which is what I was saying. Maybe you got it right, but you're saying it wrong. So you gotta have that to the in there for me to understand what you're trying to say. Let's check it. 2 to the 3 plus 1 is 2 to the 4th is 16. Kick ass. Right? So the nth partial sum is that. Neato. What is every partial sum just below? 1/2. So here's the next step. What's the limit as n goes to infinity of that? I bet you it's 1/2. It looks like it's going to be 1/2 because that's what it looks like these are all approaching, right? Every single one of these is a little bit closer to 1/2. So just looking at the pattern, it looks like the limit's going to be 1/2. Can you show me mathematically that the limit is 1/2? And that's where some of you guys freak out about the 2 to the n. Well, what can I do? Because there's 2 terms on the top and 1 term on the bottom, I can split them up. So if I want to do the limit, I can split these up. And what really nice thing happens with the second piece, for example? The second piece goes to 0 because the bottom goes to infinity, right? So this just goes away. Yay! And of course this reduces to 1/2. Right? Do you see that? Based off of what we did earlier. Because the bottom is just 2 times 2 to the n. So 2 to the n cancels, you get 1/2. So the limit of 1/2 is 1/2. Yes. It matches with what it looks like it's supposed to be doing. Thank God. I want you to kind of realize that everything I just did is what you're going to have to do with several problems just like this. You have to be able to write the elements, write the partial sums, step back and see how to write these in general, and then you can attack that form with the limit. What this means is, since my partial sums converges, my series converges. So the sum after 5 elements was 31/64. We just showed that as I let it go to infinity, the sum approaches 1/2, which means that this guy converges. Why did he have a chance to converge? What's true about 8n? What's true about these? They are going to 0. Right? So the thing that I'm adding is getting infinitesimally small. Thank God. That means that it has a chance, and we just showed it did. It has a chance to converge because these guys are getting so small. It's not going to a single number. That would suck, because then it would be infinity. Actually, in a way, it'd be nice, because then it'd be an easy question. Okay, again, how many of those kind of problems have we done yet? Okay, then, get off your own back. I see some of you guys are like, oh, I'm never going to get this. I've tried at least one of these things.